to Jairo and the organizers for putting together, as always, an excellent workshop. It's always great to be here in Schloss Waldhausen. Indeed, I can cycle here, which due to the weather I did not do today. But yeah, it's convenient on the one side. It's inconvenient in that the people at the university always think I can quickly pop back to the university. But now I've promised I'm not going to leave this until Thursday, the end of the workshop. So I'm going to be here for the rest of it. So I'm going to focus on three crucial things to make antiferromagnetic spintronics a reality, and that is reading, writing, and long-distance spin transport. And in particular, I'm also going to show some new results, some unpublished stuff, both on the reading as well as the writing and the long-distance transport. And on the reading, I'll look at bulk thin film and also new 2D antiferromagnetic materials. For the writing, we look at field and strain as well as spin-orbit torque-induced writing. And some of the results are very similar to what Markus has just shown. And finally, some new results on the long-distance spin transport in thin film antiferromagnets. So let's start with the first part, the reading. Just one slide on the types of antiferromagnets we look at are collinear antiferromagnets. And this is to do because I'm a humble experimentalist and it's very difficult to understand anything about non-collinear antiferromagnets. It's already tough enough to understand these guys, so that's what we are going to focus on. And in particular, these are the 3D metal oxides, nickel oxide, cobalt oxide, and so on, manganese telluride and manganese 2 gold. So these are the systems we look at. So the first way to read out antiferromagnetic order, because it has no net magnetic moment, is to use linear dichroism. I mean, this has been a complete eye-opener to me because it's a way to directly visualize antiferromagnetic domains. And so here you can see the spectrum taken on nickel oxide, and you can see hardly any difference, but if you take the difference, you actually do see a nice L2-3 edge. And you can image the domain structure, for instance, in nickel oxide at room temperature, at 400 Kelvin, and then at 533 Kelvin it's gone, so this is a structural defect. And this is very much in line with the nail temperature. So this allows you to actually image domains. This is an oxidic antiferromagnet. Turns out that in metallic antiferromagnets, life is even more challenging. Metallic antiferromagnets very often have very low XMLD. But for instance, manganese 2 gold, we see the domains. So you see here the nail vector, the red and the blue are perpendicular lanes to each other. And if you now turn the polarization by 90 degrees, then all that is red here turns blue here, and all that is blue here turns red here. So it's really magnetic contrast. And this is kind of what I've started to rely more and more on, because that's pretty unambiguous. All the electrical stuff is great because it's in the lab, but it's really tough to interpret. So, again, however, we don't own a synchrotron, unfortunately. So we do have to rely on electrical transport quite a lot. And then in order to actually measure the direction of the nail vector, you can use spin-Hall magnetoresistance, which was first pioneered for ferromagnets. But it also works for antiferromagnets because it's an effect that is with the cosine squared of the angle, meaning that the angle between the injected spins from a platinum or other heavy metal layer and the nail order in the antiferromagnet being an insulator or a metal leads to a difference in the resistance of the platinum. And so this was first found here in the group of E.G. Saito and the people at the Walter Meissner Institute, and there's a review here. And actually it was found also in Hamburg in the group of Hans-Peter Oepen a little bit earlier, but they didn't realize exactly what it was. So we can actually see a difference in the resistance of the platinum wire if the nail vector is pointing like this or like that. Okay. So now we use this. So the first thing we do measure is nickel oxide. So nickel oxide is a collinear antiferromagnet where the 1-1-1 planes are the easy planes, and you have opposite orientation of the spins in the adjacent planes. And then we can apply a strong field in order by the spin flop to rotate the nail vector, and we can do this along 3 perpendicular directions, the alpha, the beta, and the gamma plane. And then we can determine the change in both the longitudinal and the transverse signal. And we see that when we go to small fields, we see no change as a function of field angle. And as we increase the field from 5 to 11 Tesla, we said that the amplitude continuously goes up. And this tells you that obviously at 1 Tesla, we don't rotate much. At 5 Tesla, we rotate a little bit of the nail vector. And at 11 Tesla, we actually rotate quite a bit of the nail vector. It's actually not so easy to say exactly how much, because if you now plot the signal size as a function of angle, we see we don't actually saturate here. So there are some nicer results from the group in Munich who had access to a 17 Tesla magnet. You kind of see that it starts to saturate. What it tells you is that this is not a perfect crystal. So nickel oxide has some pinning. You don't actually rotate all the Néel vector. But there's a nice model put forward by Helen Gomenar and Hyro's group that could nicely actually reproduce the data that we had. So this is now the readout by electrical means. But if we apply such a strong field in order to orient the vector, the Néel vector, we can also do direct imaging. You can't do this in situ because the photoemission electron microscopy doesn't work in applied fields, and anyway, it's tough to do that in a 17 Tesla magnet. But what you can do is you can actually go to a high field lab, for instance the one in Dresden, apply 70 Tesla, and then go to the synchrotron. And the good thing is that if you apply 70 Tesla, you rotate very strongly pinned parts of the magnetization of the Néel vector that will stay in the direction also when you go to the synchrotron and measure it there. And so here, this is what a typical manganese to gold domain structure looks at as grown. It's roughly the same amount of domains, black and white, meaning this way and that way. And here you can see that now most of the magnetization is white. So most of the magnetization is now pointing in one direction. And you see here these little black meandering things, which are like 360-degree domain walls, or domains that point in a direction that is perpendicular to it. So even at these very high fields, at 50 Tesla, we did not make this uniform. It's another important thing to take home. It's very difficult to get antiferromagnets to be completely uniformly magnetized. In ferromagnets, if you apply a few Tesla, most materials will be completely homogeneously magnetized. In antiferromagnets, it's much tougher. Now, of course, what you would like to do is not actually having to go to Dresden to measure, to apply the field and then go to the synchrotron, but actually measure while you apply a field. And so what we did is we went to Dresden and actually applied 60 Tesla and measured during the application. Now, this is actually a very fast field pulse. It's 150 milliseconds long. And they have a nice setup where you use a high-frequency lock-in that allows you to actually measure during this field pulse. So these traces here are not only measured at different fields, but they're also measured with millisecond or sub-millisecond time resolution. And then what we see is that there is actually a relatively large change of the resistance above as you go to 30 Tesla, and then you have the spin flop transition, and then you go back and you actually change the resistance overall by something like 3%, but then at the end it only turns out that you have a very small resistance change that is residual. So there seem to be different things going on, and if you do this along different crystallographic directions, you also get slightly different behavior. Furthermore, if you actually look afterwards as a function of time, you see there's this relaxation that Markus was talking about. So actually what we see is when we apply these 50 Tesla and then wait over seconds, there is a strong relaxation where actually the signal recovers a value very similar to what you had initially. So there are actually remnant changes that are relatively modest. And if you're interested, there's more details on the poster by Stas. So originally I thought I'll explain more about it, but since Stas has a very nice poster, please go and see him. Okay, so this means we can now detect changes also during the application of the field. Now we've done this in bulk crystals, we've done this in thin films, but also now in 2D materials. So here are two very interesting 2D materials that we work on, chromium chloride and chromium thiophosphate. Chromium chloride is an antiferromagnet that is layered, which means all the magnetization in one layer is pointing one direction and all the magnetization in the other is pointing in the other direction. This means if you have a monolayer of this, it's actually not an antiferromagnet, it's a ferromagnet. If you have a bilayer, it's a completely zero net moment antiferromagnet. You have a tri-layer, then you have two layers pointing to the right, one layer pointing to the left, then it's like a ferrimagnet. So it's a pretty cool system. The main problem with this is that actually it's not stable in air, and that makes life tough. So if you want to actually measure this, you need to actually flake it in a glove box, load it in the glove box in the UHV chamber, which is not so easy to build that. So we then first resorted to looking at chemically stable systems. So this chromium thiophosphate, which has a more complex antiferromagnetic order, is a C-type antiferromagnet. And there we actually see some signals when we put some platinum on top. And so we see that there is a possibility to detect some changes. So altogether, we have different ways to read out the magnetization of an antiferromagnet, or the direction of the Snell vector. For insulators, we can use spin-Hall magnetoresistance. For metals, we can use anisotropic magnetoresistance and also domain wall magnetoresistance. Again, see stats if you're interested in this part. Imaging, which is extremely nice but cumbersome because you have to go to the synchrotron, is possible due to X-ray magnetic linear dichroism combined with some microscopy technique. Can be PEM, can be Stickson, so photo emission electron microscopy, or scanning transmission X-ray microscopy, which both work. This is a transmission technique, needs to be on a membrane. This one has problems with discharges. All have advantages and disadvantages, but they don't work in large fields. Okay, so it works. We can read out the information. Now let's write the information. Again, there are different mechanisms to do that. Field and strain, spin orbit torques, which are bulk or interfacial. So let's start with field. So I already said that by applying a strong field, we can actually change the orientation of the magnetization. So if you have an antiferromagnet which is collinear like this one, magnetization, magnetic moment down, magnetic moment up, magnetic moment down, we apply a strong field, then these can actually cant in a direction which is perpendicular to the applied field, the so-called spin flop. So if I apply a field this direction, the Snell vector will go like that. If I apply a field this direction, the Snell vector will go that. And then once it's applied, if I have the field that is very strong, you can actually cant the sublattice. So you can induce a small magnetic moment. And this helps, for instance, in order to induce a finite moment, which then makes it easier to detect or have spin-Seebeck signal or similar. Now, there's actually an interesting theory paper by Han Gomon and I that you can actually, by fields, move domain walls in antiferromagnets. It's a theory paper, which I think we still need to try. If you do asymmetric field pulses, you might be able to move domain walls deterministically. And I think that would be pretty cool. You need relatively high field gradients or fast rise time, but have a look and see if you can implement that in your lab. Okay, now let's see if that works. So here I showed you what the sample looks like after applying a strong field to induce a spin flop, where it's mostly white. And then we rotate the sample by 90 degrees to the same thing. And then we see that the XMLD spectrum changes sign. See here, first it goes down, goes up. Here, first goes up, first down, then down. So this means we have changed the net magnetization, net Snell vector by 90 degrees, just by rotating the sample by 90 degrees in the strong field. And just to check, as grown, you have no large signal. So you have an average that is roughly 0. Now, large fields, as I said, are not very compatible with our lab. So one thing that is compatible with our lab is strain. I think strain is one of the most underestimated ways to actually manipulate magnetization. So what you can do is, and this is very nice work by a former PhD student, Alexei Sapozhnik, you can actually build a device where you put a sample onto such a bar, and then by tightening the screws, you exert strain on the sample till it breaks. This is, of course, largely overestimated. In reality, you exert like 1%, 0.1% strain. So you can do that, and the nice thing is that you can actually put this into a synchrotron end station, so you can exert in situ strain while you do the measurement. So what they did is you first take an unstrained sample where you don't have any net XMLD signal, and then you apply strain, and then you see that you can get a nice XMLD signal showing that you have oriented the majority of the Snell vector along the direction of the strain, and that's due to magnetoelastic coupling. So these antiferromagnets have a big advantage and disadvantage at the same time, namely the 3D metal oxides have huge magnetoelastic coupling. That makes it very difficult to have homogeneous Snell vector orientation, because small changes in the crystalline structure lead to small strain, and even small strain can lead to large changes of the anisotropy and therefore large pinning. However, at the same time, when you then apply strain on purpose, it allows you to reorient the Snell vector. Okay, again, I mean, strain is great, but again, strain is not what a company would look for in order to manipulate the Néel vector efficiently in a microelectronics device. For that, we use spin-orbit. We've already seen nice talks about this, so I don't need to go into a lot of detail. So this was first seen in Thomas Group and in Nottingham in copper manganese arsenide. We then worked on manganese to gold, similar to what Marcus has shown, where essentially by injecting current in perpendicular directions, you can switch the Néel vector by 90 degrees. So this works, as shown here. We see that depending on the current density, we get different amplitudes. So heating effects are important. Again, Marcus explained this very nicely. And we get relatively large changes of up to a few %. So they're relatively easy to read out. So this is Néel spin-orbit torques, which are bulk spin-orbit torques, field-like bulk spin-orbit torques that only exist in these very special symmetry systems, such as copper manganese arsenide and manganese to gold. More ubiquitous are interfacial spin-orbit torques. So interfacial spin-orbit torques means you have a heavy metal layer in contact with an antiferromagnet. And then it was predicted a few years ago by the group of Kyung-Jin Lee and by Han Gomona and Hiro that when you inject inject current and due to the spin Hall effect, you generate a spin accumulation, then you can move a domain wall. Now this is great and potentially extremely fast. However, let me just show you that again, the direction of the motion of the Néel wall, of this Néel domain wall, depends on its chirality, whether it goes clockwise or counterclockwise. And that means you need to have homochiral walls to have a net direction of the motion, a net change of the Néel order direction. So this, in systems without, let's say, Lifshitz invariance or DMI, should not lead to a net change of the redistribution of the domain walls. So there is a second effect, the so-called ponderomotive force. If you're interested, the details are here. It's Helen Gomona's theory. And then when we inject in the spin Hall material a current that generates a spin accumulation, then you get to a net change of the area covered by domains, because 90-degree domain walls are affected by this. So this is all the theory. We are experimentalists, so we checked it, and we started just like what was shown by a number of groups. So in this PRL here, with Jaroslav Czakovniak and colleagues. In this paper, I think the author is here, and also by Marcus. So we have a cross, we inject current pulses along two perpendicular directions, measure the voltage, and everything happens. Great switching. So then, of course, you start with the biggest signal. It's amazing. It works really well. You get this sawtooth signal. And this, if you look at our paper here, which has been on archive for a year, and there are various versions, and you see that our interpretation has been refined over the year. So one has to say we also benefited from interchanges with various people in the community to figure this out. Now, it turns out that if you look closely at 19.5 milliamps, which is about 5 times 10 to the 11 amps per square meter, we see this triangular switching. However, if we reduce the current density just to 18 milliamps, we see this switching with the opposite sign. See here, it goes up, goes down, goes up, and here it goes down, goes up, goes down. Now, the question is, apparently two different things are happening, and you have to be quite careful, because this is only a 10% or 5% change of the current density. And then another 10% lower, nothing happens. So this is something where one has to be extremely careful. And so the question is, what do these two things do? And so we thought, okay, maybe it's all magnetic, maybe there are some structural changes. And so what we did is we actually did some imaging to make sure that actually there is some real magnetic switching. And indeed, we see magnetic switching. And the magnetic switching actually sets in at the threshold where this type of electrical signal occurs. This kind of abrupt, not sawtooth-like, but a step-like switching. So then the question is, what is the sawtooth like? And so we did some more. This is some hot of the beam time results, where we see really nice switching of large parts of the magnetization. You can identify domain wall motion and ponderomotive force effect. So both these occur, so this is really good. But how do we separate between these thermal effects and the the structural effects that Marcus mentioned and the magnetic effects? And there actually cobalt oxide is great. Cobalt oxide has a Néel temperature that is around room temperature. So we can easily measure below and above. So first we measure below. And we see, exactly like nickel oxide, we get this step-like switching, rectangular switching, or step-like switching at low current densities, and we get the sawtooth-like at high current densities. And then we increase the temperature above room temperature, and then we only see the sawtooth-like. So this here apparently is somehow an effect that has to do with the magnetic switching, and this one here occurs above the nail temperature, where obviously there's no magnetic switching happening. So this can be attributed to the structural changes, and these switching, the rectangular switching, can be attributed to magnetic switching. And this is also in line with our PEAM observations of the direct nail order reorientation. Okay, so here one has to be careful. So thanks to Marcus for this very nice introduction, and I completely agree with him that you can see all kinds of electrical signal. And just one word in addition, something we always check is, we check the size of this signal compared to what we see during field application. And when we apply field to reorient the nail transition, then we get something of that order. We never manage to see this size signal when we apply fields. And that shows you that it's likely not magnetic of origin. So I'm not saying that we figured it all out, but I think we're pretty certain there are two effects, one magnetic, one non-magnetic. Okay, so let's summarize the writing. So we can write by magnetic fields, which even though it's a hassle, it is still extremely valuable to do that in the lab in order to reorient the nail order where not much else can happen. You can apply strain. It's really interesting in mutual elastic coupling. I think it's underused. It's also not super easy. We can apply spin orbit torques, which are very fancy, easy to write, nice papers, but tough to understand because we have these bulk nail staggered spin orbit torques, we have the interfacial non-staggered spin orbit torques, and we have all the non-magnetic effects occurring due to heating, due to changes in either the metal on top of the magnetic insulator or inside the magnetic metal as well. So this is something you have to be careful. Okay, and now the last 5 minutes, just some update on long-distance spin transfer in antiferromagnets. I guess some of you have seen the presentation that we've given on the paper that we published on bulk hematite, where essentially we have two heavy metal strips on top of an antiferromagnetic insulator, which in our case is hematite, alpha Fe2O3. And then what we do is we essentially inject a current here, which by the spin Hall effect generates a spin accumulation, which then excites or populates magnon modes in the antiferromagnetic insulator. So you have a net magnon imbalance, so an effective transport of spin angular momentum due to the circularly polarized magnons to the detector. And here in the detector, these are then converted by the inverse spin Hall effect into a longitudinal current that we detect. So essentially, we keep here the current constant, we measure the voltage here, and we vary the distance between these two in order to identify the type of transport that we see. So the first important observation, and this is from our paper from last year, is that initially it looks like you might have some linear decay, but if you look for long distances, you see something which can be modeled by a diffusive transport, so you see an exponential decay. The second thing that's important is we never see a threshold current density. Our signal always scales with the current density, which then points that there is a diffusive transport where there is no threshold. There's no auto-oscillation. There is no superfluid spin current. However, the good thing is that even for the diffusive transport, we get transport over 40, now 100 microns. So we can get signals over 100 microns, no problem. And this is as good as the best ferromagnet like YIG. So, so far, people have only seen transport in over a few nanometers, like in nickel oxide. There are lots and lots of papers that have shown spin transport over a few nanometers. We show over 100 microns. So where does that come from? First, the type of transport. So indeed, we have no threshold. We have relatively high temperature and then exponential decay, which means it's diffusive transport. So there's nothing special a priori about our transport. It's not superfluid. So let's look at different types of hematite, different thin films, and see how this decay of the spin current transport depends on the thickness and on the type of hematite. So here we have C plane and R plane, just two cuts, same material, just two cuts And we see that we actually see a difference in the exponential decay, sizable difference in the exponential decay, showing that their cut is already important to determine how far the magnons propagate. However, what is still nice, even in thin film hematite, which thin films are never as good as bulk crystals, we see a spin propagation over distances of microns. So here it's up to 5 microns or so. So spin transport length scale, spin diffusion length of a few hundred nanometers. Then, if you compare this in the bulk, we saw, spin diffusion length of 5 to 10 microns. In C-cut 400 nanometers, in R-cut 600 nanometers, and in thin film nickel oxide just a few nanometers, maybe 10 nanometers. And then if we go to the spin flip transition, we actually see something that cannot be described by a diffusive transport at all. So what's happening here? So it's definitely nothing like spin superfluidity, because it actually decays much faster than the diffusion that you usually expect. So the question is, what sets this length scale? It's all hematite. So in hematite, we can get length scale from 10 microns to 50 nanometers. And so one of the things that we thought, well, can domains play a role? And there has been some nice theory work by the group of Arne Bratas, and also some other theory papers, that actually magnons, because we have a magnonic spin currents, can be affected by domain walls and can be scattered from domain walls. So let's check what the domain structure looks like in these different materials that we have. So here we have C-plane hematite, where we see that we have domains of 100 nanometers or so, and we see that we have a spin diffusion length of 50 nanometers. In R-plane hematite, we have domains of 500 nanometers, and we have a spin diffusion length of 600 nanometers. And then in R-plane bulk, we have domain sizes which are much larger than 10 microns, and we get transport over 5 to 10 microns. And in nickel oxide, we have very small domains. And so we also measure just a few nanometers of spin transport length. So what we find is, and of course, I chose typical best pictures. This value could also be a factor 2 different. But fundamentally, qualitatively, there is a correlation that we see if the domain sizes are small, we see a short spin transport length scale. If the domain sizes are large, we see a long distance spin transport. And so the theory predicts that these circularly polarized magnons can be scattered from domain walls. And if you have many domain walls, you get a lot of scattering. So you get something like a magnon domain wall resistance. So the magnons don't propagate very far if you have lots of domain walls, and they propagate far if you have fewer domain walls. So on the positive side, you can say that you can even govern the spin transport length scale due to domain walls. And actually, if you look at this paper here by Andrew Ross, Romain Lebrun, and myself, and colleagues in Trondheim and in Utrecht, you can see that actually by changing the spin structure, even within a single sample, we can change the transport length scale significantly. So we haven't yet done the kind of smoking gun experiment where we can image the spin structure and measure the spin transport at the same time. But we can say if we apply a strong field and make it more monodomain, the spins travel further. So qualitatively, it fits. Okay, now I come to the most important slide. This is the people in my group that did all the work, in particular the people here in the first row, Lorenzo Baltrati, Romain Lebrun, Andrew Ross, Christine Schmidt, and my permanent staff scientist, Martin Jordan, Gerhard Jakob, also Steph Bodnar, and Hartmut Zabel. They did all the work. I just traveled around to give talks. We have great collaborations in the groups of Gerrit Bauer and Eiji Saito in Sendai, where some of the materials and a lot of the theory comes from, with Joe Barker, formerly at Tohoku, now at Leeds. Then in Mainz, we work very intensely with Helen Gomonai, who's really been eye-opener for many of the antiferromagnetic spintronics, because she just knows it all. With Karen Evershaw-Zitter, of course with Hyre himself, Jure and Hayo also on many of the experiments on the manganese to gold. A lot of work has been done at various synchrotrons, so I'm extremely grateful for all the hard work that all the beamline scientists do. So Markus Weigand at BESSI, Simone Finizio, Jörg Rabe at PSI, Florian Kronas and the group at BESSI, Francesco Macarozzi and the people at Diamond, some theory from Uli Novak and Konstanz. We have a great theory collaboration with our colleagues at NTNU, with Arne, Ali Reza, Akash, Scott Bender, Rambert Deun in Utrecht. And for some of the terahertz work that I didn't show, we work with Tobias Kampfrath, And so to sum it up, I acknowledge support by all these organizations, and I've hopefully shown to you that we can read antiferromagnets by XMLD microscopy, which I think is very important to show something magnetic is happening. And we can use electrical spin Hall and AMR effects in order to measure it in the lab. We can write antiferromagnets using spin orbitals due to domain ball motion and quantum motive force effects, in addition to fields and strain. And finally, we can transport spin and antiferromagnets over long distances. This strongly depends on the domain structure, and the spin transport can therefore be tuned. And yeah, we also have some positions. Anyone wants to become a professor? We have an assistant professor tenure track opening. And otherwise, talk to me, and I'm looking forward to the discussion, and I thank you for your attention.
Much. Yeah. So for the last part, you mentioned the iron oxide domes. How thick are they?
So we have anything from 30 nanometers to 500. So below 30 nanometers, the problem is the Morin transition goes down. So if you have very, very thin films, you can't actually go below the Morin transition. You're always in the weak ferromagnetic phase. But yeah, so a few tens of nanometers to a few hundreds of nanometers.
So I guess the domain size also depends on the thickness.
Yes, if you give me 5 more weeks of beam time at the synchrotron, we do a systematic study, and I'd love to know that, because we have a lot more electrical data than we have imaging data. Absolutely. So, I mean, we know from the spin flop fields and the abruptness of the Morin transition that thicker films tend to have higher quality, but it's not universal. You also have difference between C-plane and R-plane, because C-plane is not chemically stable. So there are more things going on, not just thickness.
Suppose you have perfect film, let's say 30 nanometers,
yes.
Single domain versus 500. Do you think how much this thickness will limit the dissipation?
Good question. I mean, if you think that the spin diffusion goes over microns, then you have, of course, interface reflections. So then it'll play a role. It turns out that at the moment when we go to thinner films, the spin diffusion length goes down anyway, so we don't get into that limit. So we don't really have films where the spin diffusion length is much longer than the thickness where we could say it is limited by scattering at the interface. But yes, I would love to have, please make perfect films for me. But yeah, I think it's a absolutely valid point.
How about strain actually? So the nickel oxide, cobalt oxide, they are all heavily strained as bulk crystals.
Yes.
Very heavily. I think the thin films probably suppressed, but it should nevertheless be there somehow.
So I think the difference is that in thin films you get much more local strain because you just have misfit dislocations at the growth. Yeah. And at these kind of grain boundaries, even if they're highly oriented, I think that's where the strain is. And I think this is what gives you the small domains. I mean, I have no proof of that, but actually there is all these claims in the literature. If you have a nickel oxide single crystal, you pinch it with tweezers, it changes the domain structure.
Can you roll up?
Sorry?
If it's thin, it can roll up.
Yeah. So I think I agree. But I think the problem is with the thin films that the local growth defects lead to then local variations of the easy axis making the small domains.
Okay. Yeah?
So when you antiferromagnets, you know that the spin transfer length scale is lower than the domain size.
Maybe.
Ferromagnets, we can get to the domain by applying reality.
Yeah.
And still we know what spin relaxation length scale
Yeah.
is shorter than this.
Yeah.
So do you have an estimate, or is it possible at all to estimate an intrinsic spin relaxation length from this data?
Yeah, so we have this data here where what we do is we actually do some training effect, where we actually see if we cycle the field multiple times, then the signal goes up. Meaning that by applying fields multiple times, we can get rid of some of the domain walls, possibly. But then we hit some, after doing 10 times or so, it doesn't go further up. So this might be some intrinsic signal, but it might simply be that we don't have enough fields to get rid of more of the domain walls. So you'd love to do this experiment in some imaging facility where you can see how many of the domain walls you have removed. So I mean, I can tell you that in bulk crystals of hematite, it goes to 10 microns. So fundamentally, in the material, 10 microns is possible. But then, of course, you might have higher damping in the thin film. So the intrinsic length scale limited by the damping in thin films might still be lower than in the bulk. But fundamentally, in Fe2O3, you can transport spin over a length scale of 100 microns.
Okay, I'll ask another question. Magnetoelectric effects or flexoelectric effects, are these ever considered to be used for tuning your domains? Not necessarily nickel oxide.
BFO.
Yeah.
So, I mean, BFO is something that we briefly worked on. The problem is that it's already tough to understand stuff without the electric effects. I mean, there's some very nice work on these spin spirals in BFO and changing the interaction between the antiferromagnetic order and the electric effect. And I think, of course, you know, for like low power variations or manipulation of the Néel order, this would be extremely exciting. But then we need someone like yourself that knows a little bit about magnetoelectric effects. And I think it's also not so easy to control these somehow independently. I think that's tough. But I think it's obviously it's a clear avenue where to go. I mean, there are like chromium oxide. There are many materials where people have started to look into possible magnetoelectric effects in this. So.
You don't get any coffee if you stop asking.
He's desperate for coffee.
I'm not very familiar with XMLD, more with XMCD, but you show some XMLD where the L2 signal seems to be larger in black reason than the L3. Is it expected? Is it normal?
Yeah, okay. I mean, I think one should be very honest here and say that the XMLD signal is small. I mean, if you're used to XMCD signals, where you know the noise is tiny and you know the signal looks amazing, this is kind of the opposite here. The noise is large and the signal is tiny. So we've seen actually, and then also the oxidation state can change. So for us, it's a bit of black magic onto where to go to have the maximum of the XMLD effect. It seems to change from sample to sample. Sometimes there's even a feeling it changes from synchrotron to synchrotron.
But you mean between L3 and L2?
No, just where on the edge, on the rising edge, on the falling edge of the absorption peak. I mean, I think I have somewhere in the beginning, I had the XMLD. So here. I mean, you know, this kind of, the question is, where do you go? And yeah, it looks like this is even larger than this, but I'm not sure because also there's a finite, sampling size. And it might be that in between these two, there's another peak here. So, I mean, if you look at some really good XMLD spectra, this is larger than this. So, I mean, the people that do this professionally and have single crystals have looked just at the XMLD effect intrinsically. But it's not like in ferromagnets where these are like a factor, 5 difference or so. I think that's different. It also depends. I mean, now I'm talking about nickel oxide, which we looked at a lot. Already, cobalt oxide, for some reason, is tougher to image. So it looks like the XMLD effect is not smaller, but it's more localized at a certain energy. So a little bit of energy drift, which you have in the synchrotron, already destroys your contrast. So that makes it much more cumbersome, because essentially after every long exposure, you need to do another absorption spectrum to see where your energy has drifted. Like Lateral, which is not so fantastic for energy stability. Marcus is nodding. He's had the same experience. So yeah, technologically, yeah. I mean, as usual, smaller signals make life tougher.
All right, that seems to be it. Thank you very much.